Hi everybody, we are back with the seventh session of Azure AI cohort. We welcome you all with Ajay sir and Aditya sir. I hope you all are following your assignments well and on time, and I hope that you are rewatching the stream so that you get a gist of whatever is happening if you are not able to catch up live. I would like to call Ajay sir to the stage and Aditya sir to the stage. Welcome them all, and I would like to hand over the stage to them for taking up today's session.
Sure. Thank you, Guinea. Okay. Hi, everyone. Friday evening again. I think this is our last week for this Azure AI cohort. So I'm super excited for this last two sessions. Today is session 7 of this 8 session cohort. And almost we came to the end, and today it's going to be a little intense, and there are a lot of things that we're going to cover. But before going into that, let me just quickly explain what we have discussed in our last 6 sessions. Let me get into details of each session. In the session 1, we discussed about the definitions, history, background of AI, and all this machine learning, deep learning, and all this terminology in AI. And we also had a very good discussion on AI and explained some real world scenarios. And after that, in the next session, we discussed about the supervised, unsupervised learning and reinforcement learnings. And we did also a hands-on activity using the Python and scikit-learn. And after that, in the third session, we discussed about the importance of data collection, cleaning, and pre-processing. And also, we had a hands-on for that session. Also, we worked on Titanic's data set. And on day 4, we discussed about deep learning. And there we did some kind of image classification for different objects using deep learning. That's an interesting one on day 4. And on day 5, we discussed about NLP. There we discussed topics like tokenization, embeddings, and language models. And we also did some processing of news articles using this NLP. And in the last session, we did a mini project. We created a pipeline. We explained the best practices, tools for effective teamwork. And it's mostly project-oriented session, the last session that we had. And today is our day 7. And in this session, we are talking about the evaluation metrics, hypertuning techniques, and a lot of hands-on activities. So let's get started. So before we start, let me introduce myself. I'm Aditya Saladi. I'm a software engineer at Microsoft. Been here from last 5 years, 5.5 years. And before that, I've worked in Germany for my internship, and after that, worked on a couple of startups. And other than work, I'm a big foodie. So I love trying different food cuisines wherever I go. I've traveled 11 countries so far, and I share all of that stuff on my Instagram. The handle name is Code with Adi, and I have a same handle on YouTube as well. If you're interested, sorry, just give me a second. I'm getting a echo somehow. Sorry, sorry for that. Yeah, I have the same handle on YouTube. If you're interested, you can just subscribe there for Telugu content. Yep, over to you, Ajay.
Sure. Thank you, Aditya. So hi everyone. I'm Ajay. I'm a principal software engineer again at Microsoft. I started my career in 2010 from Wipro. I was a 2009 passed out. So I had a paper on cloud computing in 2009. So funnily enough, I'm now building cloud. So that's where I started. Over a period of last 15 to 16 years, I've worked with multiple big organizations. I've worked with Goldman Sachs, JP Morgan Chase in the past. In 2017, I started contributing to the developer community via a YouTube channel called Tech Primers. I used to visit a lot of meetups and companies during the last few years. In 2020, I became AWS community builder for a couple of years. Then I joined Oracle Cloud, and now I'm with Microsoft, right? So in the Azure product group. That's a bit about myself. And if you are interested in tech content with respect to system design, architecture, cloud, AI, anything, you can head to Tech Primers in YouTube, right? So with that, couple of housekeeping items for today's session, right? There are a lot of resources and goodies which we have to be given. If you have not seen these sessions, the earlier sessions, do head to github.com/tech-handbooks slash Azure AI cohort. We have links to all the resources, whatever we are covering, the hands-on code, the assignments, the submission links, the recording links for the older sessions. All these are present in this particular link. There is also a discussion forum. There is tech handbook/discussions where you can head and ask any questions if you guys want to ask, even after the session or maybe after the whole cohort, right? So do head out or reach out to us using these discussion forums. Like I mentioned, there are a lot of assignments and goodies to be won. So if you have not submitted the day 5, day 6 ones, do submit them, and learn from this whole exercise as well, right? In addition to it, as a bonus, whoever is consistent throughout these sessions and the assignments, top two of you will be getting 1 hour mentorship opportunity from both of us. So that is something which we both are giving from our end, right? So with that, for today's session, we will be covering different topics around model evaluation and optimization. So till now, what we did is we were able to create a model. We created a mini project on how to train our models and then finally create a model. But then how do we evaluate this particular model is performing well, right, with the data set, or maybe in a real time production scenario, how will we be able to identify regression out of this model, right? So we are going to see different techniques in this. The agenda goes something like this. So we will look at what are the different metrics in which you can evaluate a model. There are different techniques for identifying imbalanced data sets and then correcting them, because a lot of times when we do train these data sets on a particular model, there are chances that these data sets are imbalanced. So there are different techniques to correct that as well. There is also cross validation technique using which we can validate if all the data set which we are using to test our model is all validated, right? So there are different techniques in that. I will cover that as well. There is also hyperparameter tuning. We will talk about what is it. Again, different techniques are there using hyperparameter technique tuning. In the hyperparameter tuning, we will see that using grid search or random search, right? Finally, how do we select a particular model, and then there is something called ensemble learning, so which is a technique using which we select our model and then finally publish that, right? So this is how the agenda goes. This time today it's going to be different from compared to the previous sessions. In the earlier sessions we used to cover the theoretical part and then head into the hands-on. Today we will be doing a mix of theory and hands-ons. There are going to be 4 different hands-on sessions, so as and when I complete some theory, so we will get to see the hands-on part from Aditya, right? So that's how we can progress today's session. With that, we'll get started with the evaluation metrics. There are different evaluation metrics using which we can identify or measure a performance of a particular model, right? And these are some of them, right? Like accuracy, precision, recall, F1 score, and ROC right? Let's understand what is confusion metrics before we head into those individual terms, right? So as the name suggests, this is slightly confusing. So the idea of confusion metrics is to identify if a particular model is getting confused or not, right? Or it does, or to identify that if a particular model is making mistakes or not, right? So usually this is going to give a summary of the performance of the model what we created based on the test data what we gave to that particular model, right, as a part of testing. So it basically means that displaying the accurate and inaccurate instances of the output of that particular model's prediction, and that's what we have listed here, right? If you see here, there is actual positives, actual negatives versus positive predictions and negative predictions, right? So predictions are some things which are an outcome of the particular model's regression, and actual positives and actual negatives are the exact output which we are expecting, right? Now if you see the matrix, if we say actual positive and positive predictions, those are true positives, right? Basically whatever you thought the data would be true is all predicted as true by the particular model, right? So that's when that particular cell is getting filled, right? So you see the green ones, the true positive is filled only when like the actual data should be positive and also the predictions are also positive, right? So same way, if let's say the actual data should be negative, but then the prediction created it as a positive outcome, then we tag that as a false positive, which is FP, right? So basically the ideal output should be false, but then the prediction of the model is resulting a positive result, then that's a negative scenario. That's why it is false positive. Same way, the negative predictions, which should be like actually positive, are like denoted as false negatives, and same way true negatives when there are negative predictions on the actual negatives, right? So that is how we are mapping this whole matrix. And whenever we have an overlap between the actual positives and the actual negatives, that's where we have the green boxes, which is nothing but the successful scenario, right? So those are the different high level terms. There's also, if you look at this particular diagram, right, to evaluate individual metrics, right, like accuracy, precision, recall, and specificity, all the parameters which we require to calculate this is all within that particular confusion matrix, right? For example, let's say accuracy, right? We have been using this term accuracy for or in all our discussions, right? So how do we measure the performance of a particular model, right? So that's what accuracy denotes, right? So how does it identifies? It's basically a ratio of the total correct instances by the total instances, right? Most of the time accuracy cannot give the exact performance measure, because the model's performance is dependent on the data set which we train on, right? So it is difficult to identify using just accuracy to say if a particular model is good or not, right? So that's why we need so many different other metrics. The next one is precision, right? So precision indicates that the accuracy of a particular model's positive predictions, right? So accuracy tells us about the total correct instances. It doesn't care whether you were positive or the model was positive. It was just a whole superset. But precision says that out of the positive predictions, right, how can I identify what are my positive predictions? So if you see here, the formula for that is TP divided by TP plus FP, which basically means the total or the true positives out of the whole true positive plus the false positive, right? So you just sum these up and then identify what is the probability of it, right? So that is what precision is all about, right? Coming to recall, in the diagram, recall is mentioned as sensitivity, right? So that's another term for recall. So recall refers to the completeness of basically capturing the actual positive cases, right? So actual positive cases in the sense there is false negatives as well, right? So whatever the outcome of that particular model, right, comparing it with the actual outcome, right, we need to identify what was the real outcome of it, right? So that is why sensitivity is denoted as the true positives divided by true positives plus the false negatives, right? So that's where it just aligns with the actual crash, but the precision is aligning with the actual with the predicted class, right? So that's why you see that precision is in the x-axis and the sensitivity is in the y-axis, right? The next one is negative predictive value. If you see here, that's we don't use that much, but then just understand that negative predictive value reflects the accuracy of a model's negative predictions. So similar to what precision did for positive predictions, negative predictive value does it for negative predictions. So out of the outcome of the model, how much value is in the negative side of the spectrum, right? So that is what the NPV does, right? And finally, specificity. So specificity is again another important metric. It is used in the evaluation of classification of models. For example, if let's say I want to have a binary classification like male or female, etc., right? So in that case you can use specificity model. It usually recognizes with the actual negative case, right? So it deals with a negative case scenario, so you can use that for those kind of binary classifications. It's also otherwise called as true negative rate, right? So TNR we call it. You will see those in the coming slides, but know that specificity deals with the negative scenarios, and then it shows the true negative rate of a particular model's outcome, right? There is also type 1 error and type 2 error. If you see here, two of these tables are having type 1 error and type 2 error. What are these? These are basically an outcome of the false predictions, right? So if you remember in the previous one, we talked about the green values, right? So these are the successful ones. Type 1 error and type 2 error are basically the false positives of these particular outcomes, right? So that is what these are. And specifically on the type 1 type of error, where we say false positive on the actual data versus the predictive class, this occurs when the model predicts a positive outcome, but then in reality it is negative, right? So the model said that this is true, but then the real value should have been like false, right? So that is what type 1 errors. The opposite of that is the type 2 error, right? So basically the model says that it is negative, but then ideally it should have been positive, right? So that's the type 1 and type 2 error category, right? Those are some terms which we use again, right? So also in addition to it, there are other metrics which where only precision or only recall or only specific matrices are not helpful, right? So for example, there is something called F1 score, where when you have data sets which are imbalanced, right, or like unbalanced, right, in that case just precision and recall cannot help us, because let's imagine a case, right? I mean, let's say there are 10 different data sets, right? Within a 10 data set, the positive outcome is just 2 and then the negative outcome is 8. Then it creates a imbalanced data set collection, right? So what happens is there are chances that bias can get created as a part of the algorithms, the model's algorithm. So that is why we need a different metric to identify and measure that particular model's accuracy and evaluation, right? And that's where F1 score comes into picture. So F1 score is denoted as harmonic mean of precision and recall. So if you have the precision and the recall values, you can identify F1 score from it, right? So and this is the formula for it: 2 into precision into recall divided by precision plus recall. So that's the F1 score. Usually we balance the precision value and the recall value to have a trade-off between minimizing the false positives and the false negatives, right? So precision takes care of the false positives and recall takes care of the false negatives. So we have a mixture on and balancing factor between these two, and that's what F1 score is, right? So when you're writing or evaluating a model, you will have, like, you will create precision, you will create recall, and then you will create F1 score from it. And then that's how we identify and measure the performance of a model, right? So one last thing on the evaluation metrics is there is something called as receiver operating characteristic curve, right? ROC curve, otherwise we call that. So this is basically a plot of the true positive rate and the true and the false positive rate, right? So false positive rate was a negative positive rate which we saw earlier in the initial stage, right? And true positive rate is nothing but recall, right? So recall is otherwise called as true positive rate, and false positive rate is the measure of the actual negatives that are incorrectly identified as positive by the model. For example, the model is basically bluffing or saying something which is positive, but ideally this should have been negative, right? So that's the difference between the true positive rate and the false positive rate. And if we plot a graph between the values and the regression of these, right, of the true positive rate and the false positive rate, the plot should have a number ranging from 0 to 1, right? Now if you see here, this particular plot has a false positive rate of 1. That basically means that like there are less chances of having a negative or a incorrect value. Same way, the whole ROC curve, or the AUC is nothing but the area under the curve, right? So area under the curve is the area covered by the entire measure, right, of the true positive rate and the false positive rate. If the value of AUC is very high, basically if it is close to 1, it indicates that there is excellent discrimination power. Basically the model is very effective in distinguishing between two different classes, let's say male or a female. It can easily identify and distinguish and then predict it, and these predictions are very reliable, right? So that's what high AUC denotes, which is near to 1. Low area under curve denotes that there is poor performance of the model, and then the model can struggle with respect to differentiating between positive classes and the negative classes, right? And also the predictions may not be trustworthy. You might have seen that sometimes these algorithms like bluff, right? And we may not get the exact results, and that's why you say people say that validate before you use data from the AI systems, because there are chances that sometimes there could be like poor performance of the data set, and that's the false positive rate, right? Now coming to an example, real-time example, right? So where you can use it, right? So let's say you have a spam filter, right? I mean, take an example of our inbox, right? So we have a spam filter. We have to identify and distinguish our or classify this whole model into either like spam or not spam, right? So there could be different thresholds we can use, and over a period of time there could be different data sets which will be coming in, and based on the data set your outcome is defined, right? Whether it is positive or negative. And the thresholds can be increased depending on the training data set, and we can keep on training and making the model better and better, right? So that's what evaluation metrics are helpful with, right? For example, this is how it looks like, right? I mean, let's say your actual data overlaps with the predicted data, right? Sometimes what happens, the predicted data may not be right, and you can see this in this particular graph where there is a red a graph plot which says that the actual data right, is not matching with the predicted data, right? And then this is where we can identify and the performance of that particular model, and then we can fine tune it, right? Also, why do you think this whole area under the curve is important is because with a single value it is very difficult to compare, right, multiple models. So that is why we need a regression model, and then we need to have multiple model runs, and then we can easily compare the AUC curve with, let's say I created a model with a specific algorithm, and then I create another version of a model with a different algorithm and different training data sets, same data sets, right? Now using the same trained data sets, I can easily use this AUC measure to compare these different models and then identify if which model is performing better, and then find the performance of each of these models. The next advantage of the whole AUC is identifying the imbalanced data sets, right? When there are a lot of imbalanced data sets, right, we need to have different techniques. We will talk about these techniques in the coming slides, but using these techniques we can easily identify, and with the TFR and the FPR, we don't have to have a biased algorithm or a model, right? So that is why that is where all these TFR and TPR and FPR are getting helpful in identifying the F1 score and the ROC and the AUC scores, right? With that, I think we can get into a hands-on so that you can see how we can train our model, how we can test it, and then we can plot it using these evaluation metrics. I think initially we saw the test split, right? We will use the same, and then we can use the hands-on to like plot that. Yeah, over to you, Aditya.
Okay.
Let me
Yep.
stop.
Thanks, Guy. Let me just share my screen.
So how's my audio? Is it okay now?
Yeah, now it's okay, but
Okay.
initially it was breaking.
Oh, okay. Fine. Let me disconnect.
Hope you can see my screen now. Ajay, can you see my screen?
Not yet. I think we have to promote to stage. Maybe we need to ping
Yeah.
Guinea.
Uh, Guinea, can you please promote my screen to stage? Okay. In the meanwhile, so let me just quickly explain what is the code that we are going to discuss now. So the code is for like to demonstrate how to compute and interpret the confusion matrix that Ajay was just discussing, and not just confusion matrix, but also some metrics that are related to the confusion matrix, right? And let's take the same example as classifying the emails, whether if it's spam or not spam. Whatever code we are going to write checks how well a classification model is performing. For example, if we build a system that classifies emails as spam and not spam two categories, we have to measure how accurate it is, right? Now shows how to measure the accuracy and also other related performance metrics. So in this, first we are going to take two two variables. One is true labels and the second one is a predicted labels. These are just assumptions. We'll say if it is a spam, we'll say it's as one. Let's take a binary array which is having ones and zeros. And if it's a spam, then we'll say the value as one. If it is not a spam, then the value is zero, right? And for the confusion metrics, we'll first build the confusion metrics based on these two values, the true labels and the predicted labels. And once that is done, we'll get other metrics like accuracy, precision, recall, and F1 scores that we just discussed. And after that, we'll discuss a little about the ROC curve, and finally, we'll see how we can visualize the ROC curve, right? So these are the four,
I
five
can see
steps
your
that we are
screen.
going to do now. Yep, cool.
Yeah.
So for this session, I'm going to use Jupyter. So till last session, we were using Azure ML, but for this session, let me just get back to the Jupyter to make things easy. So so to navigate to this screen, open Jupyter and click on the Jupyter notebook. And there you can just click on new and open the Python 3 kernel. And that will navigate you to this screen. Let's check if this is working. So let's make a print statement. Okay, this is working. Perfect. So we are going to have four hands-on exercises today. So I'm like asking you to considering the time, I'm just getting the code here, the complete code, and I'll explain each and every line in this code snippet. So that will save some of our time. So this is what the line is, right? And I'm going to give you this code snippets in our GitHub repository. So once our session is done, you can just navigate to our day 7 GitHub repository and uh, like uh, check this code. So let's see what each line is in this code snippet. In the first three lines, you can clearly see we are importing the required libraries. So sklearn.metrics, this the first line is sklearn.metrics, which provides the tools to calculate performance like metrics like confusion metrics, classification report, and the ROC curve. And then we have matplot lib.pyplot, which is used for plotting the ROC curve, which is in the last step. And then we have NumPy, where we are aliasing it as NP for easy usage. So, and we use this for numerical calculations like summing elements of the matrix and getting all those metrics for the confusion matrix, right? And then the next step is sampling true labels and the predicted labels. These are two assumptions that we are having. True labels are the actual correct answers. So one means it's a spam and zero means it's not a spam. So in this case, if you observe on the true labels, we have 1011, which means, and then let me first explain what predicted labels also means. This is what model is guessing. Basically, predicted labels is the output of the model. Okay. So in the true labels, you can see 1011, but in the predicted labels, it starts with 1010, which means the fourth value, right, or the third index value, whatever is there, is a false positive, right? So um, so let's draw the confusion metrics for these assumptions and explain the same thing in more detail. So let me just quickly show you a snippet. This is the same what Ajay explained. So so it will be like this, right? If we just discuss true is zero and if it is true zero and the prediction is also zero, then we call it as true negative, right? Which means it's a true, but negative, which means it's not a spam, right? And then if it is true zero and the prediction says one, then it is false positive, right? And if it is true one and the prediction is zero, then we call it as false negative. And if it is true one and the prediction is one, then we call it as true positive, right? So this is a simple representation of what we are going to do now. So let's get back to the code, and then let's talk about how we can generate the confusion matrix. So this is the code snippet for that. So we have confusion matrix, and we are getting this from sklearn dot metrics in the first line. So we are getting that method from there, and we are initializing that to a variable called confusion underscore conf underscore metrics. And here this matrix creates the matrix with four values. One is TP, second one is TN, third one is FP, and fourth one is FN. TP stands for true positive, TN stands for true negative, FP stands for false positive, FN stands for false negative, right? And then once we have that conf matrix, we are just printing the conf underscore matrix. We'll see that once we generate the output. And then we need to extract the matrix from the confusion matrix. So this is the code for extracting the matrix. So in this, for true positive, in the diagram, whatever I've showed you, we are going to do the same thing. Hope you understand the matrix language where we have rows and columns. 00 stands for 0th row, 0th column. 01 stands for 0th row, first column. 10 stands for first row, 0th column. 11 stands for first row, first column and first row, right? So for that, we are getting the values from the conf matrix that we just created. We are getting all the four values TPT and FPFN, right? And then we need to calculate the metrics manually. So we have four metrics as we discussed. One is accuracy, second one is precision, the third one is recall, and the fourth one is F1 score. Accuracy is the total correct predictions divided by the total samples, and then the precision is of all the predictions predicted ones, how many were correct, and then recall is of all the actual ones, how many did the model catch, and then finally we have F1 score. This is kind of a score which is a balance between precision and recall. If you have to speak about the accuracy and you can only tell a single score, then you can simply go with the F1 score because it's a kind of a average out between the precision and the recall. So how are we calculating it? These are the formulas that we discussed already. Ajay just explained these formulas. The four formulas that we see. Accuracy is like TP plus TN slash sum of the conf metrics, and you can clearly read all the formulas here, right? And once we read that, then we are simply making a print statements of all those values that we generated using that formulas, right? And then we need to print the classification report. Again, this classification report is something that we are getting it from the metrics itself, from the scikit-learn.metrics, and then we are printing the classification report. Um so this, what is this classification report method does? This will automatically calculates all your values, metrics like precision, recall, F1 score, and support. Support is like how many samples for each class in a tabular format. We'll see that in the output. And then the last step would be to define the probabilities for getting the ROC curve and AUC. Again, these probabilities are predicted by the model for each sample. For example, in this, the first value that you see is 0. 0.9, which means 0. 0.9 means the model is 90% sure of email is spam or not, right? And 0. 0.1 means obviously 10% sure of if the email is spam or not, right? And then and in the end we have calculation of ROC curve and AUC. So for that, we have ROC curve and ROC underscore AUC underscore score. Again, these three are something from the scikit-learn matrix, right? And so once we have that, we are using PLT. PLT is nothing but the matplot library. We are using PLT and plotting that ROC curve. Let's quickly execute this and see the output. This will take few seconds. Yep, it's done. So first what we are doing, we are printing the confusion matrix. So we can see this is the confusion matrix, and then we are printing the values like accuracy, precision, recall. If you see the F1 score, as the precision and recall have almost 0.8, the F1 score is also 0.8. If there is some discrepancy between these two, then there'll be a slight difference in the F1 score. And then we have the classification report. This is something, these scores are calculated manually just for our understanding purpose, just to see how those formulas work. And this is automatically generated using the classification report method. So you don't have to actually, in production systems, you don't have to actually calculate all this by giving the formulas. Instead, you can just say classification report and it will does everything automatically. And here we are getting the precision, recall, F1 score, and support. And finally we are printing the ROC curve, and this is how the ROC curve is. Yep. uh, this is how we display the confusion matrix and all the matrix associated to that. If you have any questions, I'm like happy to answer them. I'm not able to see
Sure.
the chat. Let me just stop sharing and see the chat.
Yeah. Thank you, Aditya. I'm just sharing my screen. Yeah. So now whatever Aditya showed, right? So that had evaluation metrics. But then what if the whole data set, what we were training with, right, had some imbalances, right? For example, this diagram just shows that the black circles are all the majority, and then there are some minority, right? So what happens is when you have a collection of data set with both majority and minority, the whole algorithm, when you train that algorithm with this data set, it can get biased with the majority, right? For example, let's say 95% of this particular data set belongs to a negative class, right? So the whole model labels everything as negative, right? It may seem that impressively the accuracy or the accuracy of this particular or the performance of the model is at 95%. However, it isn't a genuine proficiency, right? Because there is a bias towards the whole majority, right, which is the negative scenario, right? So in these cases, like these are skewed scenarios, right, where your precision is very high, right? The primary reason for that is because of the fewer instances of the minority class, and then reducing the chances of the false positives, right? But then the recalled, which aims at identifying the true instances, right, of that particular minority class, will be very less, right? So what will happen is the precision will be high, and then the recall will be in the opposite direction, right? So this can lead to a decrease, and then there is no balance between the precision and recall, right? So that's why we need that F1 score, right? So F1 has that balance. F1 score creates that balance between the whole precision and recall. But then in order to also make sure that the data set is balanced, so we need to have different techniques which we can leverage for creating a more balanced data set, right? So one of them is the class weights. So class weights is one technique using which we can assign different weights to the classes in a particular data set, right? You can give more importance to a particular minority class during the training model. Let's say I cannot go and artificially generate some minority data set, right? So instead, what I will do is I will give weightage for my minority data set. Let's say there is two data in that whole 10 data set, right? There are 10 records, and then two data denotes the minority class, and then remaining 8 denotes the majority class. I can give weightage to the minority class so that it can balances out with the majority class, right? So that's where class weights comes into picture. So using that weights, the when the performance is generated, it gives a decent performance for us, right? So and then these performances are not imbalanced as such, right? Now how does this work is, in the real scenario is there is a weighted loss function. The loss function of that particular model is basically adjusted with the misclassification of the minority class, which is like penalized more heavily than the majority class, right? So there are penalties which are done automatically so that your minority classes are like penalized more than the majority class, right? So this can be done automatically by class weight parameter, which you can set in these algorithms, and based on that your data sets can automatically balance, right? Based on the weight loss function. So the next one is, again, there is something called balanced class weights. Some algorithms usually have an automatic way of balancing these, right? So where the class weights are based on the frequency of the classes in the data set. So automatically these algorithms can identify, okay, this much of a data set is having positive, so I can automatically balance out the class weights, right? So these class weights are automatically assigned without us going and doing any manual intervention on, like, the minority set should be given less class weights or more class weights, etc., right? So this is one technique where you can have imbalanced data and then convert them into balanced data set so that your performance can be accurately measured. The next one is oversampling or undersampling, right? So again, since we have imbalanced data set, we can over provision stuff, right? So for example, as a part of oversampling, I can create synthetics data points for the minority class. So for example, let's say there are less number of females in a particular data set. There is male and female categorization, let's say, and then there are less number of data set which has like female audience output, right? In that case, we can create the synthetic data point for that particular minority class, right? Instead of assigning the weights like what we did in the previous technique, in this technique we are going to inject some artificial data set to this. All right. There are different techniques which we can do it. For example, SMOT is one technique. We will see the hands-on in a bit, but that is one technique in the oversampling. Undersampling is, now that we have more majority class, let's try to reduce the majority class. So that's what the undersampling is. So for example, this diagram should help you understand, right? So as a part of synthetic minority over sampling technique, SMOT, what the algorithm does is, or what the library, since we are going to use this scikit-learn, there is a library to or a method which you can call, and then it does it automatically. So what it does is, it identifies that there is an imbalanced data set. If you see here, the green ones are the majority data point, majority class or the majority class. The minority ones are in the red, right? As a part of the SMOT algorithm, it can automatically generate a new synthetic data point, right? And that's what shows up in the blue, right? And now that the minority class is more, or basically balanced with the majority class, now you can have a final data set which you can train your algorithms with, right? So again, this process is like, it not just increases the representation of the minority class, but it also reduces that imbalance ratio, right? Making sure the whole data set is more conducive for the training of the AI models, right? um, with that, Yeah, let's cover some advantages and disadvantages before getting into the hands-on part, right? So now, what is the advantage of using the smart? Like I was saying, we can have an improved model performance. There is also bias which gets created. uh, when you have like major and minor classes created, like I said, there could be a bias created towards one particular category, so that also can be like neglected with the smart technique. Also the data efficiency, let's say we don't have data, we are going to artificially generate the synthetics data, so data efficiency is also covered there, right? We can have like different number of data sets created. And finally, the compatibility with various algorithms. Smart is algorithm agnostic, right? Meaning it can be used with a wide range of AI algorithms, right? For example, you can use it with decision trees, you can use it with support vector machines, right, or neural networks, etc., right? So smart is a technique or the algorithm which can go with others techniques as well, right? Now coming to the limitations as well, so smart has proven to be a valuable tool, but it is essential to be aware that there are some limitations with this tool, right? So overfitting is one risk. Like if let's say you're not carefully using smart algorithm, it can lead to overfitting as well, right? So especially when you're generating a excessive number of synthetic samples, right? So sometimes your cross validation could be like too much, right? Because I'll show that in a bit, but then it could be very cruel. It could be very crucial, and um, uh, you have to like more accurately fine tune your models and understand the accuracy from it, right? So that's where overfitting comes in. The other thing is the potential noise. There could be some data set which may not be even contributing to the outcome of that particular model's performance, right? So that's where uh, these synthetics samples could be a noise as well, right? It can negatively impact your performance of the model, right? Also finally, the choice of k, basically you can have a parameter, how many parameters you want to train with, like which determines the number of neighbors, right, which you want to consider. So you can control that, right? And also, if let's say you provide an incorrect value for this k, right, it may again lead to undesirable results, right? So those are some of the limitations of the smart algorithm. Now let's get into some hands-on to see how we can leverage this mode for balancing a particular data set which is imbalanced.
Cool, Ajay. Let me
Yeah.
just share my screen now. Gini, please promote this. Hope you can see my
Yeah.
screen.
Yeah, I can see it. Yes.
Okay, perfect. So now, in the second example that we are talking, that's smooth for balancing the data set. What's the problem? As Ajay explained, imbalanced data sets make it harder for the models to correctly predict the minority classes. So, say if there are if there is a cricket team, right, where we have only one bowler and nine batsmen, it doesn't look good, right? And you need to have a balance between the batsman and the bowler. So the solution is one solution that we're proposing is smooth, generates synthetic samples for the minority class to balance the data set. And we are going to do four steps here. One is first create an imbalanced data set where we have maybe something like a 9:1 ratio, where nine items belong to one class and one item belong to another class. And then check the class distribution using np dot bit count, and then let's apply smooth to it to balance the data set, and view the new class distribution over after oversampling, right? Let's go through the code now. Again, for the code, I'm not going to go line by line, in sense like I'm not going to execute line by line. Instead, I'll get everything here and explain it all at once. So yes, as usual, the first step is to import everything that's needed. Here we are importing two things. One is Smooth. So think of Smooth like a tool which helps you for preparing for a cricket match. The one example that we just discussed, like say one team is having one bowler and 10 batsmen, the other team is having like nine bowlers and one batsman. We need to adjust these teams accordingly, and have equal number of bowlers and equal number of batsmen in each team. To balance these teams, Smooth creates synthetic players for the smaller team based on the existing player characteristics, and it doesn't just copy the existing players, but tries to create a new realistic players, right? And and then the next line, you can see we have something called as make classification. This is a tool to create the practice data set. Think of it like making a false classroom where 90 students pass the exam, majority of the class, and 10 fail, which is the minority. We use this to practice balancing technique like smooth, and then we create the imbalanced data set. And for creating the imbalanced data set, we are going to use this make classification method. So if you look at this, there are a lot of things here. So one is n underscore class is equal to 2, which means we are saying it's a binary classification. Example, batsman and bowler, or it can be pass or fail, right? It can be like basically binary. The classes can be only two. So in case if we have three sets of classes, then we'll say n underscore classes is 3. And for showing how distinct the classes are then for that we'll say class underscore sep equal to 2. And we'll also give the weights, the imbalance that we want to create. We are going to create it at 9 is to 1 or 90 is to 10, whatever you say. For that, we are saying 0.9 is to comma 0.1. And then for showing the features that actually matters for classification, we are saying n underscore informative equal to 3. And for features that doesn't add much new information, we are saying n underscore redundant equal to 1, right? So the name itself will say if it is informative, which means it actually matters the most. If it is redundant, which means it's not much useful for our classification, right? And then the number of random samples for labels, for that we use this flip underscore y. And then we have the total number of characteristics. The name itself says n underscore features, which is 5 in this case. And then we have each class to distinguish each class clusters. For that, we'll say n clusters underscore per class, which means we are saying one class is structured like clustered together, right? And then for showing the total number, denoting the total number of students that we want to generate in this set, we can say n underscore samples. Maybe if it is like team players, maybe there will be 11 players, right? In this classroom, we are considering maybe 1,000 students, right? So we are saying n underscore samples is 1,000. And the last one, as usual, we use the random status 42. The reason is it ensures the consistent results every time we run this code. If we make next time run with random status 43, we get totally different set of results, right? And what is happening in this whole this single line of y, x and y, so we are imagining a simulation of 1,000 students where in the ratio of 9 is to 1, which means 900 students pass the exam and 100 students fail the exam, right? And the imbalance is intentional. That's something that we are creating. If we create it with 55 is to 5 ratio, which means it will be a balanced class, we are intentionally creating this imbalance. And few real-time examples other than classroom are maybe fraud detection, the email detection that we saw. Maybe 99% of the emails will be normal, 1% will be fraud, right? And disease detection, like most of the people can be healthy, but hardly 1% can have a kind of a rare disease, right? So in this, there are three key like uh, three terms that we are using. One is features, the second one is classes, and third one is imbalance. Let me just quickly explain what this three keywords means. Features are the measurable characters. It can be exam score, attendance, anything. And the classes, it can be either fail or pass or fail. It can be healthy or unhealthy, or it can be fraud or correct, right? These are called as classes. And then coming to imbalance, one category for has far fewer samples than the other. That scenario is called as imbalance. In this case, we have more number of students who are passed and less number of students who are failed, right? That's the imbalance we have, right? And then in the next line we are printing the bit count. So we see this new term called np dot bit count of y. So this counts how many students belongs to each class, whether it is pass or fail, right? And in our case it's 900 and 100, right? And why is this important? This shows us the data set is imbalanced, meaning that far more pass cases than the fail cases, and a machine learning model trained on the dataset might always predict the pass because it only sees a very few cases of fail, right? And now the main story comes. So let's apply smooth to this data set with the same random state as 42. So this is the line for that. So again, smooth is something that's coming from imb learn dot oversampling. If you don't have this installed already, you just have to say pip install imb learn. So that will install it. And you may see some difficulties with versioning between IMB Learn and Skikit Learn. So you may have to downgrade one version or upgrade one version that will make this work, right? In my case, I had to install. I don't remember the versions, but I'll mention that when I'm uploading it in the GitHub, right? So again, what does a step back, what does smooth stands for? Synthetic minority over sampling technique. And in this case we are applying smooth and we are initializing a variable called same smooth, right? And then let's see how it looks after applying the smooth. So inside the smooth we'll just say smooth dot fit resample. I think fit is something that you might have heard in our previous sessions. Whenever we have a model and we want to train the data with that model, we usually say model name dot fit of training data, and that will train the data on that specific model. In our case now, we are saying fit underscore resample. So once we apply this, let's see what happens after that. So now after that we are having np dot bit count, same whatever we did before pre-sampling. We are doing the same after sampling. Let's quickly execute this and see the output before sampling and after sampling. Now let's see, now we can clearly see the original class distribution was 900 and 100, because that's the count we gave. We gave a count of 1000, and we gave a data set of zero point 0.9 and zero point 0.1. So now after resampling, we can clearly see the distribution is equal in 1:1 ratio, which is 900 is to 900, right? So now if we train the data with this 900 is to 900, we can get proper accurate results. Yep. Over to you, Ajay.
Awesome. Yeah. So it basically created fake data.
Yeah, correct. Yeah.
Yeah. Let me share my screen. So one thing what I have realized is, since we have a lot of these data sets which we show in this algorithm, right? So we are creating a smaller subset and then we are testing it out. But then when we go live into production, right? What happens is your real data set could be huge, right? I mean, you have test data set. We are selecting only few data set to compare it, but then your trained data set is like huge, right? So if you see here, this meme
Correct.
just explains that, right? I mean, we test it with a test data set, but then your training data set is like huge. Right now, how do we even make sure the score or the evaluation technique, whatever we are going to use, whatever you are using, is all like giving us good performance for our model, right? So that is where the cross validation comes into picture. So cross validation is a technique in, again, model evaluation and selection. It helps us in assessing the performance of that particular model, but then it in a more robust and a reliable manner, right? So till now we use different techniques to do imbalance, and then we were using the train split and then different techniques. But then now with the cross validation, the way we are going to validate the test data and the on the train data and then the model, right, is going to slightly vary, right? So Aditya would have used something called as random state as 42. As the random state changes, the training and the data set changes, right? The training data set and the test data set changes, right? So basically, depending on the ratio, the test data set is picked up from that, right? And this changes the accuracy of every run, right? And every time you change it to a different random state, the accuracy could be different, right? So that is why a cross validation techniques are required to make sure that we are going to use proper prediction techniques, right? To even evaluate our models, we need a proper way to like test our model, right? So that's where these techniques are helpful. So some of them I have listed here. There are tons of techniques, right? Depending on the use cases, we can use the technique which we require. So I'll cover three of it, right? There is leave one out cross validation, right? Or we call it lockout, right? I mean LWCV, right? And then k-fold cross validation. There is stratified cross validation. There is also time series cross validation. Depending on the use cases, we can pick one of it, right? Now let me explain what is this leave one out of one out cross validation, right? So as a part of leave one out, like you see in this particular diagram, right? We are going to pick one particular subset of a particular data set. Let's say there are 10 different records or 10 different training set. Out of the training set, I'm going to pick up, let's say, one record as a data set, right? And for that, I need to iterate picking up the test data set every single time. So let's say there are 10 records. So first time I picked up one record. So I'm going to run this 10 times, and every single time, and I'm going to just leave one of that particular iteration out. And that's what, if you see here, there are different iterations here. Each of the iteration has different test data set. The yellow ones are the test data set, the blue ones are the training data set. So out of my training data set, I have picked up one as a test data set in the first time. In the second iteration, I'm ignoring that one which I already used, and I'm picking the one record which I have not used as a test data set. So that way, if you look at it, it has extensive evaluation process, right? So every data point is being validated, right? So generally what we do when, let's say, we want to buy a particular product, right? We go and look at the reviews, right? Sometimes what happens, the review is not clear. We look at multiple other reviews, right? So we look at some review, though like sometimes like the reviews are less or there are less number of stars, we sometimes go and buy a particular product, right? So validations are something similar, cross validations are something similar. So depending on the different iterations you trained with different data sets, your accuracy could be different. And since we are doing exhaustive evaluation, every data set is going to be analyzed. And again, that adds up to the disadvantage of this particular technique, because when, let's say, your data set is, let's say, 3 billion parameters, right? Now we cannot have 3 billion iterations done because your parameters are that many, right? Or your data set is that many, right? That's where we can have other techniques. One other disadvantage in addition to that computational intensity is the high variance, right? The whole performance estimates can be very high with respect to the variance value due to the high sensitivity of the model, right? With a single data point, right? Now if one particular data point or the test set is completely different from the others, right, it can completely result in a different variance output, or the accuracy, right? And also it can have bias, right? The accuracy will be very low because new data sets could be coming in, right? Because let's say the first data set or the first record which we used was a negative data set and the rest all were positive, there is a complete bias on it, right? And then the output will be completely different. The variance is completely screwed, right? So that is why this technique is not predominantly used, but then there are other techniques as well, right? This is just an example what I just explained, right? But there are 10 data sets d1 to d10, and there are 10 different iterations. The first time we do train on the 2 to 9, 2 to 10, and then we validate or basically use the test data set on the first data set. Same way for each and every iteration we pick up the next item, right? The next technique is called as k-fold cross validation. As a part of k-fold cross validation, we can pick up the number of iterations. So k denotes the number of iterations, right? So if you see here, I'm like, let's say, having 5 different iterations, so my k number is 5, right? So the model is trained on let's say k minus 1 folds, right? So for example 1 to 5, right? And these are validated on the remaining folds, right? So this process of repeating k times, right, with each of these folds used by this validation, and exactly once we are doing it, right? So this results in an average estimation, right? So it creates a averaged out value for a single estimation, right? So generally what we do is we split by k. For example, let's say there are 100 records, right? And the k value is 5. So we split the whole 100 records into 20 of five folds, right? So every iteration will have, like, if you see the individual set, right, those are 5, right? And there are 5 iterations, right? So we train the model on these and validate these model on the kth fold, right? And then we compare and then we average out these performance. So since we have created different categorization, right? For example, out of 100 records, I've created 20 records, right? So compared to the earlier technique where we picked up one by one, here we just grouped these data into one particular k fold, right? And that's what we're doing here. We just grouped by 20 here, right? um, Now that is why this technique is little bit better than that particular the previous technique. The advantages are, again, it reduces the overfitting, right? It also uses the entire data set because you're just grouping them, right? And we are going to train them on the entire data set, right? It's not just individually we are selecting it, but then we have grouped them in the form of um, folds, right? We just group them in the form of folds, right? And again, this to some extent reduces bias and the variance, which was a negative scenario from the previous technique, right? So that's why k-fold is helpful. And again, if you can ask me, like, why can't this again have a disadvantage? Again, this also has a disadvantage. What happens is, again, this adds more computational power, because when you say k value, right, when, let's say, the k requires a lot of these processing CPU processors to train our model, right? And again, it is time consuming when there are larger data sets. Let's say there is a huge data set with, like I said, 10 billion parameters, 8 billion parameters, and then your k value is less, then again it has to go through that many number of data sets, right? So that is where this particular technique could be computationally intensive, right? Again, similar to the k choice, when you have a specific value to a k variable, depending on that the output could be different, right? Which is almost similar to the existing technique where you select only one there, but here we are having k value which can be like again controlling the whole data set, and it can create imbalance as well, right? So that's another thing, right? I mean, when you are splitting by let's say 20 or 5 folds, there could be imbalanced data set coming within that particular 20 trained data or the test data, right? So that is another disadvantage of this technique. Now what can we do, right? There are a lot of disadvantages with the previous techniques. There is something called stratified cross validation technique, right? Using which you can use the same k-fold technique but then create a balance set within it, right? So what we can do is we have this classification algorithms which we use, right? Using the classification algorithms we can create a classified balance set within a particular k-fold, right? So what basically we do is let's say we have created the same 100, there is 100 data sets, and then we have 5 as the k value. So there is going to be 20 or 5 different folds, right? So within a particular 20 data set, right, within that particular fold we are going to create a classification, identify that whether this particular category has been balanced right or not, right? For example, here the categorization is male or female, right? In the earlier technique we never looked at the data within that particular 20 data set, but in the stratified k-fold cross validation we are going to look at the classification of data within that particular data set which we are going to test or train with, right? Now that is how we create a balance with a combination of k-fold technique and also with the balanced way of having the imbalanced or balanced data set when you're training it, right, within a particular fold, right? So that is what stratified k-fold cross validation is helpful with. Again, you can ask me what are the disadvantages for this. Again, this also has heavy computational power because you are going to do more of your computation within a particular fold, right? So for example, this is an example which clearly shows that there is class 0 and class 1, right? Like Aditya said, let's say there is male or female or there is batters and bowlers within a particular data set. So every data set gets split into the classification technique. So within the data set you classify that particular data set into different classes, and then depending on the classes we can identify whether it is balanced or not, right? And then use that to train our particular folds. So if we see here, based on the balance set which got created, we are going to train our model, right? And there is a k value is 5, so we are going to have k folds. So it's a merger of k fold cross validation, right? So those are the different techniques for cross validation. Like I said, there are multiple other techniques as well. Take a look at them, but I just covered 3 of them for us, right? One another common algorithm which you will be seeing throughout the whole machine learning journey or when you are training a particular model is the random forest algorithm, right? So I just want to give a refresher on the whole random forest algorithm because we will be using it while evaluating and selecting a model, right? So the whole random forest algorithm works by creating different decision trees, right? So decision trees are basically used during the training phase. So whatever data which we have, the data gets mapped in the form of decision trees, and each tree is constructed using a random subset of that particular data set, right? And this is the random range, right? I mean the random number which we said, which we put, right? This randomness usually introduces variability among this whole individual trees. It also reduces the size, the risk of like overfitting, right? So it improves the overall prediction performance of that particular algorithm, right? So that is where random forest algorithm internally uses decision trees, and all the data sets, let's say we have a list of people who have scored centuries, right? Depending on the value, let's say the score has been identified as the dataset root, right? Depending on who has scored more than 50, it goes into one particular tree, right? People who have scored more than 50, it goes into another. That way you can easily identify the batters and the bowlers, who is an all-rounder and things like that, right? So that's how your data set gets split into decision tree format, and depending on the number of tree or the max depth, right, and also the tree split criteria, there are different techniques in which you can split a particular tree. Like there is Guinea, like entropy, there are the two different techniques, and again you can the algorithm can randomly create a node selection as well, right? Based on different data sets, right? So again, lot of times when you are using random forest library from the scikit-learn library, it uses default parameters, right? Otherwise, you can also set these parameters, like I mentioned, the number of trees it needs to hold, the max depth, right? Criteria for splitting. All this can be customly provided to the algorithm. But if you're using the scikit-learn library, it can automatically have some default parameters as well. So if you are using if you have used, or if you're using a random forest library, you can see that you may not be passing all the values, but then you can customize that as well. All right. Also, the other reason why we use random forest algorithms throughout our machine learning exercises, it has a low variance and it also has a low bias model, right? It creates a technique, or it creates an algorithmic structure where you can have very less number of variance in the way you are testing your data set, and also it creates low bias when you're testing your data sets, right? Usually if you compare this with a regression model, let's say for example, Aditya will show you with the regression model as well, you can see that regression models sometimes have very high bias, but random forest algorithm doesn't have that, right? Now with that, what are the parameters? So earlier I just mentioned about some of the parameters, right? The number of the tree depth, the max depth of the tree, the number of trees within that, etc. Right? So these are different parameters which we define in a particular model, right? So same way, these there could be some parameters which can be like internal, right? Or it could be specific to the model. For example, there are weights and bias during the whole machine learning exercise, right? These models or these parameters are created, right? And these are internal models or internal parameters which are specific to the model. So they are either called as internal parameters or model parameters. There are also some parameters called as hyperparameters, right? So these are parameters which are external to that particular model or algorithm, right? Which we define customly. For example, I want to create a learning rate, right? How is my algorithm learning, right? How is my model learning or training, right? There could be epoch value I want to generate out of it. There could be number of neurons in each layer I want to create from a neural network model, right? I want to understand how many layers are there, right, etc. So these are some custom parameters, and these are called as hyperparameter, right? So the reason for tuning that is, these are configuration variables which are set before a training process, right? And they can control the whole learning process in itself, right? And if you don't tune them, it could go in different direction. So the
Ajay, you are
whole
breaking.
hyperparameter tuning. Oh, okay. Is it fine now?
Yeah,
I
now it's
think
better, but
yeah, sometimes, yeah, I
for
think sometimes it
for
my
like
internet is
10
flaky,
15
I think.
seconds, I wasn't able to hear you.
Oh, okay, okay, okay. Thank you. Yeah. So hyperparameter tuning is basically the process of selecting optimal values for a machine learning model. And these are machine learning models hyperparameters, right? So like I said, learning rate, epoch or neurons in each layer, these are all different um, parameters. And then you can tune these, right, based on our model and how we want to tune them. There are different techniques for that as well, right? So for example, let's start with grid search, right? So grid search is one exhaustive search technique. We can evaluate all possible combinations of hyperparameters within a particular specific range, right? Let's say I have 100 data sets, right? If the 100 data sets are too huge, I can provide a particular range in which I want to have my searches done, right, within that particular set. For example, 20, if I give 20 is the specific range, the system builds a model for every combination of this hyperparameter specified within that range. For example, in the tree scenario, right? Let's say I want to have like ranges of like 10, 20, and 30. These are different values on the trees, right? And also I want to have like max depth of 3 or 4. So what grid search does is, for every single data set combination, it tries to plot that into a matrix. So if you see here, what it has done is, it is trying to do all the possible combinations of hyperparameters which are there. For example, there is max depth here and there is estimators here, right? So we are mapping that, and for each and every possible combination, it's trying to plot and then run that particular algorithm. So earlier what we were doing is, we were doing the cross validation, we were running some algorithms, right? Now imagine that data set, the trained data set and test data set, which is done for multiple other combinations of hyperparameters, right? So based on the different parameters, we are going to repeat the whole exercise which we were doing till now n number of times. The algorithm which Aditya showed running it, imagine that getting run for each and every time, and then the values are getting plotted in a particular matrix or a grid, and that is what this is, right? And out of which one of them could be a best result, right? So basically, grid search is a method for hyperparameter optimization, which involves in specifying a list of values for each of the hyperparameter. Like I mentioned, I can define max depth. The depth here is 5, and then there is estimators, which is like again, let's say 5, right? I mean, for simplicity, it's a 5 cross 5 matrix here, so we're just saying 5 and 5, right? So based on these values, right, we can optimize our hyperparameters, right? A simplest set could be like, for example, male and female, right? If I want to have my hyper parameter which defines a gender, right? So based on the gender, I can easily identify and run this whole grid search algorithm, right, which will train the model using these combinations of male and female category data set, so that you can evaluate the performance of each of these model using this particular range, right? So the optimal values for hyperparameters are then obviously chosen from these module performance of this model, right? There is a library called as grid search CV. Again, there is another a library called as random search CV in the scikit-learn, which is what you will see in the coming slides. But before that, let's look at random search as well. Now that we understood how grid search works, in the grid search you had a combination, you gave a subset on which this particular combination should work on. In the case of random search, this particular combination is not given to the algorithm, so random search is like automatically picking up these efficient um, um, ways in which grid search was built. So grid search was building on top of how it can create a grid with possible combinations based on a data set which it was provided with. But with random search, it will just pick up these values randomly, and then it will create a search algorithm based on the um, optimal values for the hyperparameters which are chosen, right? And then the outcome of it is again plotted with a grid, and then the best result is like picked up from there, and then that is how we can identify the effectiveness or the performance of that particular data set or a model, right? Now the advantages and disadvantages of these techniques are listed here. So for grid search, it is very comprehensive and simple to implement. On the other hand, like the disadvantages of the grid search are like it's very computationally expensive, right? Because you have a specific combination, right? And you have to do that for every single time. And then there are a lot of scalability issues which you get when you use grid search. When you're using random search, right? Random search is efficient than grid search because it does exhaustive search for every combination, but it finds good parameterized values, right, randomly, right? I mean, unlike the existing grid search where it has a combination which is predefined, here we are going to randomly pick data. So randomization creates more authenticity, and it can create good parameters out of it, right? Right, and again, it can be scalable when you have high computation systems, and when you have more dimensions, right? When you have multiple dimensions and multiple combinations, random search is much helpful, because in the grid search, when you have huge data set combinations, it can result in like very huge expensive data runs, right? Again, disadvantage for the random search is you may miss some of the data set because it's random. So there are possibilities that some samplings are missed out when you are performing these searches, right? When you're performing or running these algorithms, right? And also the results can vary between the runs due to the randomization of the nature, right? And that is why the results could be like stochastic. Like basically sometimes you can get a result which is like somewhere down the line, and then it could be like high or low, right? So that is the difference between random search and grid search. Right, whatever I just said is just like plotted here in the summary, right? The efficiency, if you look at it, the efficiency is low in the grid search. And also, when will you go with grid searches? When you have smaller and medium data sets, grid search is a good choice, because the data set is very small and medium, and the probabilities or the specific ranges are like quantifiable, right? And they are like easily like controllable, right? When you have like larger data sets, you can go with random search, because when you have larger data sets with multiple dimensions, right? Unlike the category which I said with gender, male and female, if you have multiple categorizations, then it makes sense to go with the random search, right, to have more efficient algorithm run. There is also Bayesian search, right? I mean, Bayes search, right? So this is also another way of efficiency identifying the performance of a module. If let's say you want to identify how efficient my particular model is performing, right, then you can use the Bayes search. But generally, most of the time we use grid search and the random search, right, depending on the use cases. And then if we need any complex ones, we go with the Bayes search. With that, I think we'll get into the hands-on for the grid search, right? Let me stop my screen.
Sure. Let me share my screen now. Mm, let me know once that is visible.
Yep, I can see it.
You can see the Jupyter nodes, right?
Yeah, yeah, yeah.
Okay, cool. So, right. So what are we going to do now? We are going to do the hyperparameter tuning with grid search. So we are building a machine learning model using a technique called random forest. And the goal is to train the model using the data set, not the real data. We are going to use the simulated data in this case. In all our previous examples, we were using real data from Kaggle or any other open source. But for now, we are going to use just the simulated data and use a method called grid search to find the best settings, nothing but the hyperparameters for the model, and test the model on unseen data to see how well it performs, right? And again, these are the three major steps. So for the code, let me just get the code all at once instead of breaking this into pieces, and explain you what each of these sections do, right? So the first one is obvious, importing um, of all the required libraries. The first one is Grid Search CV, which helps find the best settings in for the model. And the second one is Random Forest Classifier. We've already Ajay just discussed this already. This is a machine learning model we are using. And then make underscore classification. This is something that we used in our previous example. This creates the fake data set for us to work with. And then we have train test and train underscore test underscore split. If you are following my all our sessions regularly. In every session, we are using this training and splitting from scikit-learn model selection. This will help us to split the data, one into training set and the other one into the testing set, right? And then let's create the data set. For that, we are using two lines of code. These are the two lines. So what is happening here? We are initializing first in the first line. We are initializing x and y, and we are creating a fake data set using make underscore classification method, which is coming from this scikit-learn sklearn dot datasets. And here we are seeing three parameters. One is n underscore samples, the other one is n features, and then the random state. Here we are n underscore samples denotes 500 data points, 500 rows, and n underscore denotes features denotes the number of columns. Here we are creating 10 features. Features can be like the scores, attendance, anything, right? And then label y is for denoting whether it's like the binomial thing, whether it's a pass or fail, right? And we split the data into the training data set and the test data set. Here in this case, we are saying the test size is 0.3, and the which means the training size is 0.7. So which is like 70% of training data and 30% of testing data. And in both the lines, we are seeing a statement called random state. Again, this is something that we use for reproducing easily, right? And then we have defining the model and the settings. So this is where we are defining the model and the settings. So what is happening here? We create a random forest model. This model works like a collection of decision trees. Each tree gives it precision, and the forest takes the majority vote. So we define the settings for testing, and that settings are given in the variable called param underscore grid. And this is having three settings. One is n underscore estimators, the number of trees in the forest. We are saying 10, 50, and 100. And then we have max depth, how depth each tree can grow, which is like 5, 10, and 20. And then we have min underscore samples underscore split. This is the minimum data required to split the tree node, which is like 2 comma 5 comma 10, right? And why test these settings? Imagine like maybe baking a cake, right? So if you're doing it for the first time, you might test different baking timings, temperatures in the oven, right? And ingredients, like say in the YouTube video, you might see use 10 grams of this and 5 grams of this. You may feel like that's not tasty in the first try. You think maybe 6 and 4 will work good. Next time you try with the different temperature settings and different ingredient ratios, right? And then finally at some point you find a perfect combination. Similarly, we are going to do a similar thing here. We test these hyperparameters to find the best combination, right? And then use the grid search to find the best settings. So we are using these two lines for grid search. So first line is grid search CV. This is not any custom class. This is coming from scikit-learn model selection, right? And here we see three parameters, four parameters actually: estimator, param grid, and CV and scoring. So param grid. So basically, this grid search CV tries every combination of settings from param grid. So example can be 10 trees, depth of 5 example, right? And CV5, which means it divides the whole training set into 5 parts. Trains on the 4 parts and validates on the fifth one. Like say first time in the first iteration, it can train on 1 to 4 and test on 5. On the second iteration, it can train on 2 to 5 and test on 1. In the third iteration, it can train on 1, 3, 4, and 5 and can test on 2, right? In that way, it will break the whole data set into 5 pieces and keep this on a loop and repeats this process repeats all these combinations to get the reliable result. And finally, we say grid search dot fit of x train comma y train. This fits trains the fit basically trains the model in the training data. And finally, once all this training is done, we'll print the best parameter and best score. So you can see that in this 2 lines. So best parameter, we get it from grid underscore search dot best params, and for the best score we get it from grid underscore search dot best score. So what is this best params? This shows the best combination of the settings, which are nothing but the hyperparameters. So one best parameter can be like n estimators can be 100 or max depth 10 and min sample split of 2. Let's see what comes in the output. And maybe the best score can be somewhere around 0.9 or 0.95 or 0.96, whatever is the best score, right? And at the end, we'll also test the best model. For that, we have this 3 lines. So the best in this we have what's happening here. The best estimator, the variable that you see here, grid underscore search dot best estimator. This is the model trained with the best settings, and then you see score of x test comma y test. This tests the model on the unseen testing data and finally get the test accuracy. It can be again anything between 0 to 1, maybe 0.8 or 9 or whatever. Let's quickly execute this. Let this execute, may take few seconds, but before that, let's understand why this is important. Like say in the real world scenario, suppose you are building a system to classify the emails as spam or not. You need to find the best settings to for the model to maximize its performance. And this grid search CV helps to you automatically process instead of guessing. This might be the random set, maybe the first set of results, the first set of training data can be random set, or maybe the second part of training data can be random set. You don't have to do all these guessings anymore. You can simply say grid search CV on the data and you can find the best set for training, right? And the second main thing is to avoid overfitting, and the third one is to have the better model performance. Let's see the output now. So now, as per the output, you can clearly see the best parameters are with max depth of 10 and min sampling sample split of 5, and the n estimator is 50. You can see all those parameters that we gave in this. This combination is working the best when it did the grid search CV, and the best accuracy is 0.94, which is greater than the test accuracy, right? If you generally do it, this is what we get, 0.92. But now that we have done all this grid search CV, we are getting a better accuracy of 0.94, which is 0.02 percent better than the actual accuracy that we would have got without this grid search CV. Any questions? Feel free to drop it in the comments. Ajay, over to you.
Awesome, thank you. Yes, I think we saw too many topics this today.
Right, right,
Yeah. Now, I think just to summarize all these, right? So the whole model selection process summarizes the whole problem definition, right? For example, we were talking about the initial data set, like, I mean, what type of classification are we going to do? What type of regression are we going to do, right? So we have to define a problem. Let's say I have a data set for, let's say I have a credit card. I have already got a lot of credit cards. Now I want to apply a new credit card, right? I want to create a model which can go on identify if I can assign or if I can allow somebody to own a credit card or not, right? Depending on different data set, right? Imagine that that's the problem. Now for the candidate models, we can create a different candidate models. For example, there are linear models, we can use decision trees, we can use neural networks, right? Depending on the prior knowledge of what that particular base model is, we can create a candidate model, and then we can train with our data set. Like I said, if let's say I have like a lot of customer data based on the spending pattern, right, and the credit card or the loan payment pattern, I can create or maybe for example in India we have something called CIBIL score. Based on the CIBIL score, you can inject all this data into the model as a part of a data set, and then we can use cross validation technique, right, to, for example, k-fold technique is there, stratified k-fold is there. We can evaluate the performance of each of the applicant to identify that based on the training data set, how is that particular person's value is like fit. For example, is he able to get a credit card or not, right? I mean, can we reject him for new credit card or not, right? Or maybe for no loan, etc., right? The next step is the hyperparameter tuning based on the model's outcome. Now how do I know that this particular model is performing well? We just now saw the grid search technique. We can use grid search or random search or the Bayesian search technique, right? We can properly fine tune these so that the models can give a best results out of it. Finally, we have to evaluate these models. So we can use different evaluation techniques, which we saw. We can use accuracy, precision, recall, F1 score for classification, right? Or we can use some other technique for regression, and then we can compare these models, right? So Aditya will show that in a bit on how you can compare these models, right? And based on these values, the best balanced model, based on the performance, interoperability, and the resource requirements, we will be able to um, create and choose a best model from it, right? So that is how you select a model. There is also a technique which I wanted to like highlight. There is something called ensemble learning. If you had seen that library usage of random forest, it comes from the ensemble folder package, right? So the reason for that is ensemble learning is a technique which combines multiple models, right? Usually these are called as like weak learners. I mean, it's generally called weak learners, where you can have different models trained, and then you can create a final model from it, right? Imagine it like how you have parallel runs, right? So you can have parallel runs, and then you want to like finally assemble them together, right? So that's what ensemble is, right? So we are creating more robust and accurate model by having multiple models run, and then using this data we learn from it, and then we have meta learner concept. There is a metadata which we create out of it, and then finally we create a model which can be more performance efficient, right? And this whole ensemble learning has multiple techniques. The first one is bagging technique. It's otherwise called as bootstrap aggregating, right? So bagging basically involves training a model with multiple instances of the same model on different subset of the training data set. For example, in the hands-on example we saw, right, in the random forest technique, we created the grid search, and then we gave it to the algorithm, right? So where we had multiple instances of the same data set, and these are different data sets, but then the same model is being trained with, right? And also then we finally average out these predictions, right? So um, that's where random forest is very helpful, and this is called as bagging, right? So basically you create you have the data set, you split them into multiple bags, right? You split them into multiple data sets, and then you train your algorithm based on it, right? So in our case we use decision trees based on, and decision trees helped us in creating bags, right? So that's why it is called as bagging. The next one is boosting. So boosting essentially is like a sequential model, sequential training process, where each of these models are trying to like correct the errors in one step or the other, right? So for example, I train my data set with one particular algorithm, I find out errors, and then in the next particular model training topic, I can go and correct that, right? Unlike the earlier methodology where you can do parallel stuff like uh, do things in parallel, right? Here you have to do things in sequel, right? So that's where boosting comes into picture. There are multiple algorithms or techniques which in which you can use them, like there is something called ada boost, right, which is nothing but adaptive boost. There is also gradient boosting technique, and then extended gradient boost technique, which is xg boost, right? And the final technique is called stacking. So imagine it like a merger of all these, right? I mean, you want to have multiple model outputs, you want to get performance from multiple model runs multiple ways, and then finally you want to like combine all these different model types into one, right? So that is what stacking is all about. Right, so stacking just combines different models, and then you can leverage individual strengths, and then it can lead to better overall performance because you can have an average of all the models outcome. right? So these are different techniques which fall into the ensemble learning, and you can use these techniques to finally compare and then find a best model for your use case, right? So finally we're going to end with hands-on on the logic regression with random search, right? So that's where I think we'll end here today. With that, I'll stop sharing.
Sure. Let me just
Yeah.
share the screen. Let me know once you can see
Just a
the
second.
Jupyter node.
Sure. Sure. Yes, I can see it.
Um, you can see that. Okay. So
Yep, yep.
what are we going to do now? The next exercise is on comparing the models. We are comparing two models. One is the logistic regression, and the second one is the random forest. So let me just quickly get the code there. Okay. So let me explain all the steps, the four steps that we're going to do here. First one, as usual, we are going to import the necessary libraries. Here you can clearly see there are three main libraries. One is the logistic regression, second one is random forest classifier, and the third one is the accuracy underscore score. So what is logistic regression? This imports the logistic regression algorithm. It's a simple, fast, and commonly used machine learning model for classification problems. And the second one is the random forest classifier. This imports the random forest classifier, a more advanced model that uses multiple decision trees for better accuracy. And finally, we are importing accuracy underscore score from sklearn.metrics. This is a function to measure how accurate a model is by comparing the predicted results and the actual results. So what are we going to do with all this? We compare these two models, both logistic regression and the random forest, and determine which one performs better on our data set by measuring their accuracy. So are we going to use any existing data set? No, we are going to use a random data set that we just created in our previous example. We are going to use the same data set and train our model. For that, this is the line to train logistic regression. So in the first line, you see log underscore reg equal to logistic regression with a random state of 42. Again, random state is enables us for reproducing the same set of results again with the same 42 number, right? And it creates a logistic regression model. And then we say log underscore reg dot fit of x train and y train, the same data that we are using in the previous example. This trains the logistic regression model using the training data, which is X train and the Y train. And here is the model. Here the model learns the patterns in the data to classify the new samples correctly. And then we have X log underscore reg underscore preds. Uh, it's log underscore reg underscore preds of X test. So this line is used for training the model to predict the labels of the test data, which is nothing but X underscore test, and the predictions are scored in log underscore reg underscore preds, right? And why are we doing this? We are trying and testing the logistic regression to evaluate its performance and compare it with the random forest. Then the next step would be to train the random forest. So for that, we have three more lines. These are the three lines. So in this, we are giving a random forest variable and initializing the random forest classifier with the random state of 42. And this creates a random forest model. And the random forest is kind of more complex algorithm that combines many decision trees to make predictions. And in the next line, we are fitting the data, which is nothing but fitting is nothing but training the data on this specific model. And then we are making the predictions with dot predict, right? And why are we doing this? We want to again train and test the random forest to see how well it performs and then compare with the existing results of the logistic regression. And then the last step would be to compare the accuracies. For that, we are going to use the accuracy score, which we imported from sklearn.metrics. So for there are two things. One is for comparing the logistic regression. The second one is for comparing the random forest regression. You can clearly see the variables there. And once we do the accuracy score calculation, we'll be printing we'll print both the accuracies using the print statement. Let's quickly run and see what is accuracy for both of these models. So now you can clearly see the logistic regression is having an accuracy of 0.866, and the random forest accuracy is somewhere around 0.92. Obviously, which means that the random forest is performing better than the logistic regression, right? The reason is, as we discussed, random forest is kind of more complex and a little advanced than the logistic regression. At the same time, it also consumes a lot of compute. So it's always a discussion between whether it's compute or the compute versus accuracy. So based on the business decision, we'll go either with the logistic regression or the random forest accuracy, right? So yeah, in the similar way, you can do the like create a simple test data which is close to your production data. Instead of doing all these exercises on your production data, you can just use this dummy test data and apply some good algorithm to find the right set of data for training, and then use that data on top of multiple algorithms and find which algorithm is performing better on your data, sample data, and use that algorithm for your production. This is how you can train and test and identify which algorithm works for your data. Yep, that's all from me. I think this is the longest session we had so far in all the 7 sessions. I think till now the longest one is 1 hour 26 minutes. This went for 1 hour 35 minutes already.
Yeah, yeah.
So yeah, yeah,
I hope like
that's
people
all
found it interesting.
from me.
Yeah, because we had a lot of hands-on. I think they can go and reference it. I'll make that repo public as well. So folks, if you
Yeah,
guys want to take a look at the repo, you can take a look at it as well with the code,
yes,
whatever Aditya showed.
and
Yeah,
one quick announcement.
yeah.
Yep. Thanks, Ajay. And one quick announcement. Our We are still open for the assignments for week 2 and week 3. We are closing it at tomorrow morning 9 a.m. IST, and we'll be announcing the winners for week 2 and week 3 by tomorrow evening. Right. So if you haven't already submitted it, please do submit it. We'll do all the evaluation after morning 9 o'clock and announce the winners tomorrow at 7 p.m. Anything else, Ajay?
So I think that's all for tomorrow's topic. I think we have a lot of interesting discussion. I mean, if you guys are watching it offline, I mean, if you guys are interested in having any discussion with us, because we have a lot of interesting things to cover tomorrow, right? The topic would range from emerging trends to the career advancements. What are the roles of AI in the career space and how you can leverage them? So we'll have good interaction, and also we'll show some of the Azure AI stuff, how we can look at the latest stuff what Microsoft is building to build the AI topic of interest for us for any learnings, right? So yeah, we are looking forward to it for tomorrow on the final session. Yeah,
Yep, yep, yep.
that's
Thank you so much, Ajay.
thank you, Aditya. Yeah, thank you, Ginny.
Thank you.
Yeah, done, right? Sorry, I had muted it because of some things going on in the background. All
No
done?
worries. Yep, we are
Yes.
good
Yeah.
to close.
Okay.
Yes.
Thank you so much, guys, for taking up the session yet again. We really thank you. Our audience really thanks you, and as your developer community too. I hope everybody enjoyed the session and everybody is keeping a check on the assignments given by our mentors. I'm looking forward to see you in the next session. Thank you so much, sir.
Thank you. Thank you.
Thank you. Bye bye.